Welcome. This is a video on the derivatives involving exponential functions. Okay, so in this lesson, we're going to be learning about how to take derivatives of exponential functions, and we're going to start with the most common exponential function, which is e to the x. Okay, so e to the x is a special function because the derivative of e to the x is actually equal to itself. So the derivative of e to the x equals e to the x. And in fact, that's one reason why we learn about the number e in pre-calculus. Remember, e is equal to 2.71, something like that, and it goes on forever. And it's a very special number because that function has a derivative which is itself. And it actually turns out that if you integrate e to the x, you also get e to the x. So it's a very special function that way. So remember, e is going to be 2.7121. I forget how it goes, but most calculators have e as a button. In fact, I think even the calculator that comes with this computer, once I have it in the scientific mode, see it has E as a button. So here I can just press E, and it's 2.71828, and it goes on forever. Okay, so E is approximately 2.71828. And it goes on forever, and it's called the natural base. It's also the base for a natural logarithm. Okay, so remember, a logarithm ln of x is the same as log base e of x. Okay? But that's all pre-calculus stuff. Okay, so e is called the natural base. E is called the natural base. Okay, and remember that a natural logarithm, ln of x, actually has a base of e as well. Okay? Alright, so it's a very simple formula. The derivative of e to the x equals e to the x. Now, of course, if you have something more complicated than x, so let's say you have e to the u, where u is some function of x, then the derivative of e to the u is going to be e to the u, but then you have to use the chain rule. So remember, the chain rule says you take the derivative of the outside function, inner left alone, and then you multiply that times the derivative of the inner function. So this is going to be e to the u times u prime. Okay, so d dx of e to the u equals e to the u times u prime. Probably the easiest formula in all of calculus. Okay, so let's see some examples of using this new formula. Okay, examples. Instructions are find the derivative. Find the derivative. Okay, and for problem number 1, we're going to be doing the derivative of y equals 10x e to the 2x minus 5 e to the 2x. Okay, so y equals 10x e to the 2x minus 5 e to the 2x. Okay? Alright, so we have a few things going on here. First of all, this is a product because we have two separate functions of x multiplied together. So here we have 10x times e to the 2x. So there we're going to use the product rule. So here the product rule says if you have u times v, then the product rule says that uv quantity prime equals uv prime plus u prime v. Okay, so we're going to do the product rule for this first term here. Okay, so here u is 10x. So to calculate u prime, I can write that over here. So u prime is going to be the derivative of 10x. And remember, the derivative of a constant times the variable is just a constant. So this is just going to be 10. Okay? And then v prime is going to be the derivative of e to the 2x. Now remember, the derivative of e to the whatever is e to the whatever. So up here we were calling it u. E to the u, the derivative of that is e to the u times the derivative of u. So this is just going to be e to the 2x times the derivative of 2x. Okay, so we're going to have e to the 2x times 2, because the derivative of 2x is 2. All right? So for our product rule, we need our u and our v, which I labeled here, and then we calculated u prime and v prime. And instead of writing e to the 2x times 2, we can write 2e to the 2x. So v prime equals 2e to the 2x. All right, and then we can go ahead and plug everything in to the product rule. Okay, so the formula is uv prime plus u prime v, so that's going to take care of this first term. All right, so our derivative is going to be dy dx equals uv prime, so that's going to be 10x times 10 plus u prime v. So 10x times 10 plus, oops, no, I'm wrong there. So let's see, u we said was 10x, and then v prime we said was 2e to the 2x. My bad. So we have 10x times 2e to the 2x. So what I'm doing right here is uv prime is u, which is 10x, times v prime, which is, we said was 2e to the 2x, plus u prime v. So that's going to be plus 10, because u prime is 10, times v, which was e to the 2x. Now that's the product rule. That takes care of this first term, but don't forget we also have a second term over here that we have to take the derivative of. So to take the derivative of negative 5e to the 2x, the negative 5 is a constant, so it stays out front. So let me zoom out a little bit. So we just keep the negative 5 out front. And then remember, the derivative of e to the whatever is e to the whatever. So we're going to have negative 5 e to the 2x. But then because of the chain rule, we're going to have to multiply this times the derivative of 2x, which is 2. So it's going to be negative 5 e to the 2x times 2. So this part I just did here didn't use the product rule. This is the second term here. That's what we're working on. So that part in blue, the negative 5e to the 2x, that's what I wrote down here. Whereas in red here, this is the product rule. Okay? And then we can simplify this a little bit. So this is our derivative, but we want to go ahead and multiply things out and combine like terms. Okay, so here 10 times 2 is 20. So for our first term, we have 20x e to the 2x plus 10 e to the 2x minus 5 times 2 is 10 e to the 2x. Okay? So we have 20x e to the 2x plus 10 e to the 2x minus 10 e to the 2x. And then we can see that the 10 e to the 2x and the minus 10 e to the 2x are like terms and they're opposites, so they cancel out. Okay, so we're left with 20x e to the 2x as our answer. Okay, so our answer is dy dx equals 20x e to the 2x. Okay, so that's our first example. Hopefully that's helpful. All right, so let's go on to example number 2. Okay, so example number 2. This one is y equals the quantity 4 plus 16x times e to the negative 4x. Okay? So there's a couple ways you could do this problem. The first way would be to just use the product rule the way it's written. Okay? And then the other way would be to distribute and then use the product rule for the second term. Either way is fine. However, I think I'd rather just use the product rule the way it's written. So that's what I'm going to do. Okay, so we have two things multiplied together. Each one is a function of x. So I'm going to go ahead and use the product rule again here. So labeling stuff, here we have u is going to be 4 plus 16x, and then v is going to be e to the negative 4x. Okay, and then the product rule says that uv prime, so uv parentheses prime equals uv prime plus u prime v. Okay, so over here I can write out what u prime and v prime are. So u prime is actually going to be the derivative of 4 plus 16x. So the derivative of 4 is 0 because 4 is a constant. And then the derivative of 16x is just 16 because the variable goes away. So we get u prime equals 16. And then for v prime, remember the derivative of e to the u is e to the u times u prime. So here it's just going to be e to the negative 4x times the derivative of negative 4x. So that's going to be times negative 4. Okay, so that means our v prime is actually going to be negative 4 e to the negative 4x. Okay, and for this problem, we only had the first term. So we just had one term here, so we're just going to be using the product rule here. Okay, so what we've got here is our derivative, dy dx. dy dx is going to be uv prime plus u prime v. So plugging in, u is 4 plus 16x. V prime, we said, was negative 4 e to the negative 4x. And then we have plus u prime v. So that's going to be plus 16 times e to the negative 4x. Because u prime is 16, and then v is e to the negative 4x. Okay, so we've got our derivative down here. And then, of course, you want to simplify it now. And here you do want to distribute. Okay, so we're going to go ahead and distribute the negative 4 e to the negative 4x to each of these terms. Okay, so that's going to give us 4 times negative 4 is negative 16 e to the negative 4x. Minus, well, what's 4 times 16? I believe it's negative 64. So we're going to have negative 64 x e to the negative 4x. Okay? And then don't forget we still have a positive 16 e to the negative 4x at the end here. Okay? And if you can't do multiplication like that in your head, you can always write it out or just type it into a calculator. But I'm pretty sure that 4 times 16 is 64, so I'm good. Okay, so what we got here is a couple of like terms. So we can see that the first term and the last term are both like terms because they have the same exact variable expression. Okay, so negative 16 e to the negative 4x and positive 16 e to the negative 4x, those cancel out because they're opposites. All right, so that leaves us with our answer, which is negative 64 x e to the negative 4x. Okay, so that's our derivative dy dx. Okay, cool. So that's example number 2. So you should be good there. And then I wanted to do an example that has trig functions, just in case you don't remember how to take the derivative of trig functions from calculus 1. Okay, so for example number 3, we're going to be doing the derivative of y equals e to the 3 theta times a quantity cosine of 3 theta plus sine of 3 theta. Y equals e to the 3 theta times a quantity cosine of 3 theta plus sine of 3 theta. Okay. All right, so for this one, once again, you're going to want to use, you're either going to want to distribute at the beginning or just go ahead and use the product rule. Me personally, I think I'd rather use the product rule because if you distribute the e to the 3 theta at the beginning, then you're going to end up having to do the product rule twice, which can be kind of long and confusing. So I would recommend just using the product rule the way it's written. Okay, so once again, we're going to label everything. So here, our first factor is u, so that's going to be e to the 3 theta. And then our second factor is going to be v. So here, v is going to be cosine of 3 theta plus sine of 3 theta. Okay, so once again, we have a product, so we're going to use a product rule. So uv quantity prime is equal to uv prime plus u prime v. And of course, to do the derivative of cosine and sine, you need to remember the formulas for those. So what are those formulas? They're from calculus 1, but you might not remember them. So from calculus 1, recall the formulas for the derivatives of cosine and sine. So recall that d dx of sine of u, d dx of sine of u equals cosine of u times u prime. That's with the chain rule built into it. But if you get your u's and your v's confused with all this stuff, instead of calling it u, we could just call it x. So d dx of sine of x equals cosine of x. Okay, but just remember, if you have a composite function, so if you have a function of x on the inside, you're going to have to multiply cosine of x times the derivative of the inside. Okay? And then also, the other formula from calculus 1 that you may or may not remember is the derivative of cosine. So d dx of cosine of x, the derivative of cosine of x, is actually negative sine of x. All right? So those are formulas from calculus 1. In fact, all of these are formulas from calculus 1. But we're going over it because sometimes people forget those things, because it's been a while since some people have taken Calculus 1, so that's why I like to review everything in Calculus 2. Okay, so now we have those formulas, so we can go ahead and take this derivative. So we have our u and we have our v. Now we need to calculate u prime and also v prime. So over here, let me zoom out. Over here, u prime is going to be the derivative of e to the 3 theta. So remember, the derivative of e to the whatever is e to the whatever times the derivative of whatever. So it's going to be e to the 3 theta times the derivative of 3 theta. Well, here theta is our independent variable, and the derivative of 3 times theta is just going to be 3. Okay, so here our u prime equals 3 e to the 3 theta. Okay, and then for v prime, we actually have to take the derivative of 2 functions added together. But remember, if you have 2 terms or 2 or more terms, you just take the derivative of each individual term. So here to do v prime, let's start with the derivative of cosine of 3 theta. So the derivative of cosine is going to be negative sine. So it's going to be negative sine of 3 theta. But then we have to use the chain rule. Because this is a composite function, on the inside we don't just have x, we actually have 3 times theta, which is sort of like 3x. So you have to multiply times the derivative of the inside function. So it's going to be times 3. Okay, so that's the derivative of cosine of 3 theta. And then we also need to do the derivative of sine of 3 theta. Okay, so once again, that's a composite function. So you take the derivative of the outer function, inner left alone, and then you multiply times the derivative of the inner function. So the derivative of sine is cosine. Okay, so we're going to have positive cosine of 3 theta. That's the derivative of the outer function, inner left alone, and then we multiply this times the derivative of the inner function. So the derivative of 3 theta, once again, is just 3. So this is times 3. Okay, so we have v prime equals negative sine of 3 theta times 3 plus cosine of 3 theta times 3. And people usually bring these 3's in front. Okay, so they would write it as negative 3 sine of 3 theta plus 3 cosine of 3 theta. And that's our v prime. Okay, so now we're ready to go ahead and plug in everything into the product rule. Okay, so our dy dx is going to be uv prime plus u prime v. Okay, so dy dx, using the product rule, is equal to uv prime plus u prime v. So we said u was e to the 3 theta. So we have e to the 3 theta times v prime. V prime we just calculated was this whole thing here. So negative 3 sine of 3 theta plus 3 cosine of 3 theta. Negative 3 sine of 3 theta plus 3 cosine of 3 theta. Okay, so that right there is actually our u and our v prime. Okay, so that's uv prime. We're doing the product rule here. And then we're going to have to do this plus u prime v. So that's going to be plus, well, u prime is 3e to the 3 theta. So we have plus 3e to the 3 theta. That's our u prime, right up here, 3e to the 3 theta times v. And v is this whole thing, so cosine of 3 theta plus sine of 3 theta. Okay, so cosine of 3 theta plus sine of 3 theta. So this whole derivative is huge. In fact, I got to zoom out so that we can see the whole thing on one screen. And it might have been good if I had gone to a separate line for part of this, but hopefully you can still read it. So you got our uv prime plus u prime v. Okay, and then of course we still need to distribute. So we're going to go ahead and distribute the e to the 3 theta over this first set of terms, and we're going to distribute the 3e to the 3 theta over the second set of terms. Okay, so let's focus on the first set of terms, and then we'll look at the second set. Okay, so here, distributing the e to the 3 theta, we actually get negative 3 e to the 3 theta times sine of 3 theta. And then we have plus 3 e to the 3 theta times cosine of 3 theta. So this one's quite messy. So all I did there was I distributed the e to the 3 theta to each of these terms. And then rather than writing the whole thing horizontally because it's hard for us to read, now I'm going to write the other terms down here. Okay, so over here we have to distribute our u prime. So we have to distribute 3e to the 3 theta to each of these terms. So we're going to get 3e to the 3 theta times cosine of 3 theta. Okay, so we're going to have 3e to the 3 theta times cosine of 3 theta. And then distributing the u prime over here, we have 3e to the 3 theta times sine of 3 theta. Okay, so plus 3e to the 3 theta times sine of 3 theta. And I wrote them above each other just so that there would be enough room to write it on one screen. That way we can actually read it, hopefully, on YouTube. Okay, so what we got here is now we have some like terms. So what are the like terms here? Well, we've got the negative 3 e to the 3 theta sine of 3 theta, and then we have a positive 3 e to the 3 theta sine of 3 theta. So those are like terms. And because they both have a coefficient of 3, but one of them's negative and the other one's positive, those two are just going to cancel out. So we can cross those out. And then our other like terms here are going to be the 3 e to the 3 theta cosine of 3 theta, and this one is also positive 3 e to the 3 theta cosine of 3 theta. So those are also like terms. They have exactly the same expression for variables, so they are like terms. But here they're both positive 3, so we're going to be doing 3 plus 3, which is 6. Okay, so after all of that, we're going to end up with 6 e to the 3 theta cosine of 3 theta. All right, and that's actually, it's not dy dx. I made a mistake up here. I said dy dx, but remember our variable here is actually theta. So instead of saying dy dx, I should have written dy d theta. That's my bad. I was just focusing on the math, and I'm used to writing x as my independent variable. So sometimes it's easy to forget that your variable changes on some problems. But here it should actually be dy d theta. Okay, so we have dy d theta equals 6 e to the 3 theta times cosine of 3 theta. And that's a bit of a longer problem, but hopefully you were still able to follow it. It's kind of a review of stuff from Calculus 1. Alright, so I wanted to do a little bit more challenging problems. I know that one was kind of long, but a lot of these problems are a bit longish. So let's do another one. I'm way zoomed out right now. Let me zoom back in a little bit. Okay, so for problem number 4, we're going to be doing the derivative of y equals cosine of e to the negative theta to the 5th power. Okay, so y equals cosine of e to the negative theta to the 5th power. So if you remember the chain rule and the power rule and the derivative of cosine, this shouldn't be too bad. However, it can be challenging if you're not sure how to do the chain rule. So remember, the chain rule says from Calculus 1 that you start with the outside function and you work your way inward. Okay, so here we're going to have to do the chain rule actually a total of 3 times. So we have to do the derivative of the outside function, and then the derivative of the middle function, and then the derivative of the inner function. So there's actually 3 functions in one here. So the chain rule basically says take each derivative working from the outside inward. Working from the outside inward. Okay, so you start with your outermost function, and then you do your middle function, and then you do your inner function. And you take the derivative of each function, and then you end up multiplying them all together. Okay? So what we're going to be doing here is we have 3 functions in one, so that's why we're using the chain rule. You always use the chain rule if you have a composite function. Okay? So the outer function is cosine, the middle function is e, and then the inner function is negative theta to the 5. So what's this going to look like? Well, we're going to start with, let me zoom out a little bit. Our dy dx is going to be, for starters, we're going to take the derivative of the outer function. So here the outer function is cosine. Okay, and from above, you should know that the derivative of cosine is negative sine. Okay, so we're going to have negative sine of e to the negative theta to the 5. So what I did there was I took the derivative of the outermost function and I left the middle and the inner function alone. Okay? And now we take the derivative of the middle function. So here the middle function, I'll circle that in blue, the middle function is actually e. And it's e to a power. Okay, and remember the derivative of e to the whatever is e to the whatever. Okay, so we're going to have e to the negative theta to the 5. Okay, e to the negative theta to the 5. So what I did there was I'm doing the chain rule and I'm working my way from the outside inward, taking the derivative of each function. So now we took the derivative of the middle function, which is e to the whatever, and so we got e to the negative theta to the 5. Now our last function is the innermost function. So that one is going to be the negative theta to the 5. Okay, so in green there, what's the derivative of negative theta to the 5? Well, there we're just going to be using the power rule. So remember, the power rule for derivatives says you bring the exponent out front and you decrease the exponent by 1. So this is going to give us negative 5 theta to the 4. And when you're doing these, you don't have to use different colors like me. I just like to use different colors so that you can see each part that I'm working on. So I did my outer function, which was cosine, took the derivative of that. Inner middle and inner functions were left alone. Then we took the derivative of the middle function, which was e, and the derivative of e to the whatever is still e to the whatever. And then I multiply that times the derivative of my innermost function, which is negative theta to the 5. And the derivative of that, using the power rule, bringing the exponent out front, we get negative 5 theta to the 4. So those can be tricky, but once you understand how they work, they're actually pretty quick to do. We're already pretty much done with the problem. We just need to kind of change the order around a little bit. So the standard way to write it is you write notice that these minuses are going to cancel out. We have a minus sign and then a minus 5 theta to the 4th. So these are going to cancel out. So our answer is going to be positive. And then we're going to go ahead and bring the 5 theta to the 4th into the front. So we're going to have 5 theta to the 4th. And then next we're going to have our e to the negative theta to the 5th. And then last we have sine of e to the negative theta to the 5th. And that's just following the order that they use to write everything in my math lab. That's why I'm rewriting it in this order. So they write the constant first, then they write the variable to a power, then they write exponentials, and then they write trig functions in that order. But it would probably accept it on my math lab if you used this order. I'm just trying to write it the same way they did in case you use their examples. Okay, so this is our answer. 5 theta to the 4th times e to the negative theta to the 5th times sine of e to the negative theta to the 5th. Okay, so let's see some more examples, because examples are always helpful. Okay, so problem number 5. I keep zooming out. I should probably try to zoom in more. Okay, problem number 5. So for this one, we have y equals ln, so natural log of 7t e to the 2t. Y equals natural log of 7t e to the 2t. Okay, so hopefully you watched one of my earlier videos on the derivative of natural logs. So recall that ddx of ln of u is going to be 1 over u times u prime. Okay, so the derivative of natural log of whatever is 1 over whatever times the derivative of whatever. So here our u is actually going to be the 7t e to the 2t. Okay. So what we're going to have to do here is we're going to have to do the chain rule. So first we're going to take the derivative of ln, which is going to be 1 over. All right, and here our independent variable is actually t. So we're going to have dy dt equals 1 over 7t e to the 2t times the derivative of 7t e to the 2t. So I'll just write a prime there because we haven't taken the derivative of this part yet. So that's our 1 over u times u prime. Now to take the derivative of 7t e to the 2t, we're going to have to use the product rule because we have two things multiplied together here. So a lot of problems in this section use the product rule. Okay, so the product rule, here we have u times v. And don't get this u confused with the u up here. This is going to be a different u from the one we were using for the formula of ln. Okay, so uv prime is going to be uv prime plus u prime v. So this whole thing right here is going to be uv prime plus u prime v. And then we're going to put parentheses around that. And then we still have a 1 over 7t e to the 2t. Right, so we did the derivative of the natural log, but now we actually have to do the derivative of this product here. So that's why we're using the product rule. Okay, and then if I go over here, I can actually write out my u prime and my v prime. So here my u prime is going to be the derivative of 7t, which is 7. And then my v prime is going to be the derivative of e to the 2t. So remember, the derivative of e to the u is just going to be e to the u. So that's going to be e to the 2t. But then using the chain rule, we have to multiply this times the derivative of the inside function. So the derivative of 2t is going to be 2. So v prime is going to be e to the 2t times 2. In other words, 2e to the 2t. Okay? So now we've done all that. Now we can plug in u, v, u prime, and v prime. Okay, so let's do that all down here. So we've got 1 over 7t e to the 2t times uv prime. So that's going to be 7t times 2e to the 2t plus u prime v. So that's going to be plus 7 times e to the 2t. Okay, so we have 1 over 7t e to the 2t times uv prime, so that's going to be 7t times 2e to the 2t, plus u prime v, so that's plus 7e to the 2t. And this right here is actually our dy dt. Now you might hope that you were done with the problem, but they do actually want you to distribute here. So we are not done actually. So we're going to go ahead and distribute. We're going to distribute the 1 over 7t e to the 2t to each of these denominators. Okay, so when we do that, we're going to get 7t times 2e to the 2t. So that's going to be 7 times 2 is, actually we'll just leave it that way. We'll just leave it as 7t times 2e to the 2t. I'm not going to bother multiplying it out. Over 7t e to the 2t. Right, and then for our second term, we're going to have plus 7 e to the 2t over 7t e to the 2t. Every time I say 7t, it kind of sounds like I'm saying 70, but I'm not. I'm saying 7 times t. Okay, and now we can finally cross stuff out. So here, for the first term, the 7's cancel, the t's cancel, and the e to the 2t cancels. So for our first term, we're actually just going to have a 2. Okay, so our first term is going to be 2. And then for our second term, some other stuff cancels out. So the 7's cancel out, and the e to the 2t's cancel out. So remember, if you cross out everything, but your variable's in the denominator, you're left with a 1 on the top. So this is actually going to be plus 1 over t. All right, and that's going to be our answer. So dy dt equals 2 plus 1 over t. And I think in our book, they would write the variable before the constant, so they would switch the order in which they're adding here. So for our final answer, we're going to rewrite it as 1 over t plus 2. Because remember, when you're adding, the order doesn't matter, so you're allowed to switch the order around. Okay, so our answer is going to be dy dt equals 1 over t plus 2. Pretty cool, huh? All right. So, nobody really likes the quotient rule, but we should probably do a problem involving the quotient rule. I mean, maybe some people like it, but most people hate the quotient rule, myself included. However, it is important, and we should do at least one example of it. Okay, so example number 6. Example number 6. We want to find the derivative of y equals ln of e to the 13 theta over 1 plus e to the 13 theta. Okay, so y equals natural log of parentheses e to the 13 theta over 1 plus e to the 13 theta. Now there's a few ways you can do this. One thing you could do is you could do long division over here, if you remember how to do that, and you could simplify the inside. However, I think I'd rather just go ahead and use the quotient rule, because everybody should know about that, and the quotient rule is important, so we should do one example involving the quotient rule. All right, but first of all, we have a composite function here. So we need to take the derivative of the outer function, inner left alone, and multiply that times the derivative of the inner function. So here our outer function is ln, and then, so that's our outer function. And then our inner function is this whole thing, the e to the 13 theta over 1 plus e to the 13 theta. Okay, so using the chain rule, we take the derivative of the outer function, inner left alone, times the derivative of the inner function. So because our variable is theta here, we're going to have dy d theta equals, well, the derivative of ln, or natural log, is 1 over. Okay, so we're going to have 1 over this big mess here. So 1 over e to the 13 theta over 1 plus e to the 13 theta. Okay, so that was the derivative of the outer function, inner left alone, and then we need to multiply this times the derivative of the inner function. So we need to multiply this times the derivative of e to the 13 theta times the derivative of e to the 13 theta over 1 plus e to the 13 theta. So I'll just write a prime there. So this is probably the toughest problem on this particular homework. But your one on the homework is similar to this. You'll just have, slightly different numbers and stuff. Okay, so we took the derivative of the outer function. That was done right here in red. I circled it in red. And then now we have to work on the derivative of the inner function. And the inner function is kind of the annoying part here. Because we have a quotient we're dividing, we're going to have to use the quotient rule. Okay, and I myself always forget the quotient rule. But we're going to go ahead and do that in blue here. So quotient rule. You use that whenever you're taking the derivative of a fraction. And you have a variable on the top and the bottom. Okay, so the quotient rule says that u over v, quantity prime, is equal to vu prime minus uv prime all over v squared. And the only reason I'm sure I got it this time is I looked it up recently. And remember, if you ever forget any of these formulas, you can always Google them. And I'll also be putting up a formulas sheet pretty soon in one of your modules that'll have all these formulas for you. In fact, I think I'll put it on this module. Okay, so we've got vu prime minus uv prime all over v squared, where u is the top and v is the bottom. So here our u is going to be e to the 13th theta, and then our v is going to be our denominator. So here our v is going to be 1 plus e to the 13th theta. Okay, so there's our v. So just like with the product rule, it's important to label everything in terms of u and v, and then to calculate your u prime and your v prime over on the side or on the bottom, and then plug everything in. Okay, so since we've got our u here and our v there, now we need our u prime and our v prime. Okay, so over here, I'm going to be doing, let's start with u prime. U prime is going to be the derivative of e to the 13th theta, which is going to be e to the 13th theta times the derivative of the inner function, which is just going to be 13. So u prime is going to be 13 e to the 13th theta. Okay, and then surprisingly, v prime should be exactly the same thing here. Now why is that? Well, the derivative of 1 plus e to the 13th theta, well, the derivative of 1 is just 0, because the derivative of any constant is 0. So we're really just taking the derivative of e to the 13th theta, which once again is going to be 13 e to the 13th theta. Okay, so here, this doesn't always happen, but occasionally you get this where u prime and v prime are actually the exact same thing. All right, so that'll at least make it easier to plug it in. So let me zoom out so we can see all this. Okay, so what we got here is the quotient rule. So we have u over v quantity prime equals, let me just erase that. I'm just going to go ahead and write the vu prime minus uv prime all over v squared. So we've got 1 plus e to the 13th theta, that's our v, times u prime, which is 13 e to the 13th theta. Okay, that right there was vu prime. And then we have minus uv prime. So minus uv prime is going to be minus e to the 13th theta times 13 e to the 13th theta. Okay, let me zoom in again since we got room now. And then this is going to be all over v squared. Okay, so we just said that v was 1 plus e to the 13th theta. So in our denominator, we're going to have 1 plus e to the 13th theta squared. So parentheses squared. Now this one is very complicated, I know. That's why a lot of people dislike or even hate the quotient rule, myself included, but it is important to do one of them. So we should be good here for all this, but we probably want to simplify a little bit before we plug it back into this original problem. So to simplify it, we can go ahead and distribute this 13 e to the 13th theta to each of those terms. Okay, so we're going to distribute this 13 e to the 13th theta to each of these terms. Okay, so that's going to give us 13 e to the 13th theta plus 13 e to the, well, remember if you're multiplying exponentials with the same base, you add the exponents. But here, I think I'd rather just write it as e to the 13th theta squared. You could also write it as e to the 26 theta if you added the exponents. But since we're multiplying here, I think I'd rather just leave it as e to the 13 theta squared. Okay, and then over here we have minus e to the 13 theta times 13 e to the 13 theta. So that's going to be minus 13 e to the 13 theta, where the e to the 13 theta squared, because there's two of them. Now once again, you can also add those exponents, so you would get e to the 26 theta. That would be fine as well. But remember, if you square an exponential, you're multiplying times 2, and 2 times 13 is also 26 theta, so that works as well. So what we got here is we can see that this term and that term are opposites, and they have the same coefficient, and they're also like terms. So the 13 e to the 13 theta squared and the negative 13 e to the 13 theta squared are just going to cancel out. So we're going to be left with 13 e to the 13 theta on the top, and then on the bottom we have the quantity 1 plus e to the 13 theta quantity squared. Okay, so that was just our quotient rule. So this is a tough problem. It's got a lot of steps. So this was our u over v quantity prime. Okay, and since we got that now, that was the derivative of our inner function. That's what I circled here in blue. So this entire thing, this inner function, has this derivative. 13 e to the 13 theta over 1 plus e to the 13 theta quantity squared. And then we also have this red part, the outer function. So that's going to be 1 over e to the 13 theta over 1 plus e to the 13 theta. But remember, if you do 1 over a fraction, you flip it over and multiply on the top. So for this one, I'm going to go ahead and flip it over. Go and flip this one over. All right, and then combining all this together, we've got our dy d theta equals the red function times the blue function. Okay, so let me write that down here. So we have our dy d theta equals the outer function, that outer derivative. So when we flip that over, we're going to get 1 plus e to the 13 theta over e to the 13 theta. 1 plus e to the 13 theta over e to the 13 theta. That's our outer function, so I'll do that in red just so that you can see it. And then the derivative of our inner function was that huge thing that we just did in blue for the quotient rule. So everything canceled out, and then we got 13 e to the 13 theta over 1 plus e to the 13 theta quantity squared. So I'll write that one over here. So we have 13 e to the 13 theta on the top, and then on the bottom we have the quantity 1 plus e to the 13 theta quantity squared. Well, all that work, and then at the end here, a bunch of stuff is actually going to cancel out. So what cancels out here? Well, we notice that we have an e to the 13 theta on the bottom and on the top, right there. So we can cross out those. And then you should also notice that we have the quantity 1 plus e to the 13 theta on the top, and then the quantity 1 plus e to the 13 theta squared on the bottom. So those are exponentials with the same base, so we subtract the exponents. In other words, the square and this thing is going to cancel out, and we're just going to be left with a 1 plus e to the 13 theta on the bottom. If you subtract the exponents, it's actually 2 minus 1 on the bottom, so the exponent is going to be 1 on the bottom. So now that I've crossed everything out, I have my final answer. So whatever I didn't cross out is what's left. So we got 13 on the top, and then on the bottom we have 1 plus e to the 13 theta. So that's a pretty tough problem, just because it involves so many steps. But that's about as hard as it gets on your homework. Okay, cool. All right, well, I've gone to an hour now, but I still need to cover a little bit more. So we've just talked about the derivative of e to the x or e to the u. That's the natural base. But what if your base isn't e? What if you have any other base? Well, new formula. Okay, so new formula. We said the derivative of e to the x is e to the x. So what's the derivative of a to the x, where a is any number? What's d dx of a to the x? Well, it turns out that you end up needing a different formula. Now I could prove this, but the proof's a little bit long, and I'd rather just focus on the formula itself. So it turns out that if you're taking the derivative of a to the x, you end up with a natural log of a times a to the x. So it's almost the same as the derivative of e to the x. It's just you end up needing a natural log of a out front. Okay, so d dx of a to the x equals ln of a times a to the x, where a is any number. Okay, so a is any number. I mean, of course, you wouldn't want a to be 0, because 0 to any power is just going to be 0. But other than that, a can be any number. So, so we'll say a is any number besides 0. And I guess I also should add that a can't be negative, since you can't take the natural log of a negative number. Okay? Okay, so I could probably squish that down and just say that a is greater than 0. I probably should have just said that from the beginning, but oh well. So I'll just go ahead and erase that and write a is greater than 0. Okay, but you won't have to worry about that too much in the problems. So anyway, d dx of a to the x equals ln of a times a to the x. Now, the reason for this is actually pretty simple, and I'll show you why it works that way in the first example that we do. Okay. But normally you'll just want to use the formula. Okay, so example, find each derivative. Find each derivative. Okay, for problem number 1, we're going to find the derivative of y equals 20 to the x. Okay, so if you want to just use our new formula, that's the quickest way to do this. So here our base a is going to be 20. Okay, so here 20 is our base. So here a equals 20. So writing down the formula, d dx of a to the x is ln of a times a to the x. So here that's going to be dy dx equals 20 to the x times ln of 20. Or in the reverse order, ln of 20 times 20 to the x. Okay? ln of 20 times 20 to the x. Now the only thing to realize here is on your homework they do write the ln of 20 at the end. I'm not entirely sure why they do that, but for their answer they're going to write dy dx equals 20 to the x times ln of 20. Ln of 20, yeah. Okay, so that's the easiest way to do it, is just with the formula. Now, where did this formula come from? You might be wondering why this is true. So I don't usually spend a lot of time on why, but this one's easy enough that I'll just go ahead and do it. So why is this true? Well, what you can do is, instead of writing it as the derivative of 20 to the x, you can write y equals 20 to the x. Instead of that, you can write y equals e to the ln of 20, e to the ln of 20 to the x. Now, why is e to the ln of 20 the same as 20? Well, I don't know if you remember this from pre-calculus, but this is one of the formulas for natural logs in pre-calculus. E and natural log are inverse functions, so you compose them with one another and they cancel out. So e and ln just cancel out and give you 20. Okay, and then here, what do you do if you're raising an exponential to a power? You just multiply the exponents. Okay, so what we actually have here is y equals e to the x ln of 20. Okay, I can write it like that because we're just multiplying these exponents here. All right, and then how do we get from this to 20 to the x ln of 20? Well, we just take the derivative. Okay, so here our derivative, dy dx. Using the chain rule, we take the derivative of the outer function, which is e, and we know that the derivative of e is just itself. So our outer function is still going to be e to the x ln of 20. But then we have to multiply this times the derivative of the inner function. But remember, ln of 20 is actually just a constant. So the derivative of a constant times a variable is just going to be the constant. So when we do the chain rule here, and we multiply this times the derivative of x ln of 20. So I'll write x ln of 20 prime. This x goes away, and we actually just get ln of 20. Okay, so that's how we end up with e to the x ln of 20 times ln of 20. But then with the e to the x ln of 20, once again, we can just rewrite it as the way it was originally, which is 20 to the x. Because remember, e to the ln of 20 to the x is the same as 20 to the x. Okay, so this right here, I can rewrite it as e to the ln of 20 to the x. But that's just the same as, if I cancel out the e and the ln, that's just the same as 20 to the x times ln of 20. And that's what we got. But of course, as usual in math, the reason why things work is a lot longer than just using the formula. So that's why I usually just cover the formula. So here we've got our new formula, and now you can kind of see why it's true. And you can do this in general for a, where a is any number that's greater than 0. Okay? Cool. Wow, this has got to be one of the longest videos I've ever made. I'm already at 1 hour and 9 minutes. But there's still a couple more problems I need to do. Okay, so example number 2, using our new formula for the derivative of an exponential with any base. So this one, we want to take the derivative of y is equal to 3, I'm sorry, not 3, 7. Y equals 7 to the square root of s. I was on the wrong problem. on my notes here. Okay, so we're doing y equals 7 to the square root of s. And I have trouble writing s on this tablet, but hopefully that looks like an s and not a 5. Okay, so we have y equals 7 to the square root of s. Okay, so here we have a composite function. So once again, we want to use the chain rule. So we take the derivative of the outer function, inner left alone, and we multiply this times the derivative of the inner function. So we're going to get dy ds. Remember here our independent variable is s. Dy ds equals the derivative of the outer function. So here the outer function is 7 to the inner function, and the inner function here is going to be root s. So what's the derivative of 7 to the whatever? Well, we just said that the derivative of a to the x is ln of a times a to the x. So here a is going to be 7. So we're going to have ln of 7 times 7 to the root s. Ln of 7 times 7 to the root s. So all I did there was I took the derivative of the outer function, inner left alone. Now I multiply this times the derivative of the inner function. Okay, so we're going to be multiplying this times the derivative of the square root of s. Now some people who are sharp on their Calculus 1 may remember how to do this already, but some people might have forgotten. So how do you take the derivative of a square root? Well, you have to write it as a 1/2 power. That's the trick. Okay? So over here, recall from Calculus 1, the square root of x is the same as x to the 1/2 power. So square root is the same as the 1/2 power. So instead of writing the square root of s, we can write it as s to the 1/2. And then we can just use the power rule. So remember, the power rule for derivatives says that you bring the exponent out front and you decrease the exponent by 1. So I bring this 1/2 out front and I decrease the exponent by 1. Okay, so we're going to get 1/2 s to the negative 1/2. 1/2 s to the negative 1/2. All right, and then remember that if you have a negative exponent, you can move it across the division bar, and that makes the exponent positive. So we can move this s to the negative 1/2 to the denominator. Okay, and then it's going to become 1 over 2s to the positive 1/2. But s to the positive 1/2 is just the same as the square root of s. So we're actually just going to get 1 over 2 times the square root of s. 1 over 2 times the square root of s. All right, and then of course we still have the outer function here. I just got lazy and I stopped writing it. But we still have the ln of 7 times 7 to the root s. Okay. So we still have our ln of 7 times 7 to the root s. So there's our dy ds, and then we just want to rewrite the order a little bit, just so that's a little bit easier to read. Okay, so rewriting the order the way they do online on my math lab, the way they would write this is they actually write the ln of 7 in the numerator, they write the 2 root s in the denominator, and then they bring the exponential out front on the right side. Okay, so we've got ln of 7 over 2 root s. They write that as a fraction. They put parentheses around the fraction. And then they bring the 7 root s out front. Okay, so they bring our 7 root s over here. Okay, so there's our dy ds. I really hate s's because I always make them look like 5s and then I have to fix them. Okay, but that's our final answer. So we've got the quantity ln of 7 over 2 root s times 7 to the root s. Okay, just a couple more examples. Okay, so example number 3. We want to find the derivative of y equals 6 to the z to the 6th. The derivative of y equals 6 to the z to the 6th. Now, if you've been paying attention to the rest of this lecture, this hopefully shouldn't be too hard. So we take the derivative of the outer function, which is 6 to the inner function, and then here our inner function is z to the 6th. So this one's actually should be a little bit easier than the last problem. So what we've got here is dy dz, because our independent variable here is z, equals the derivative of the outer function, which is going to be ln of 6 times 6 to the z to the 6th. So that was the derivative of the outer function, inner left alone. And now we multiply this times the derivative of the inner function. So we're going to multiply this times the derivative of z to the 6th, which, using the power rule, we just bring the exponent out front and we decrease it by 1. So we bring this 6 out front and we decrease it by 1, so it becomes 6z to the 5. Okay? And that's almost the whole problem. This one's actually pretty straightforward. So now we've got dy dz equals, well, the order they write it in on my math lab, they write the 6z to the 5th first, and then they write that times 6 to the z to the 6th, and then they write that times ln of 6. So natural log of 6. And I just realized my 6's look like b's as well, which is, oh well, what are you going to do? Okay, cool. So 6z to the 5th times 6 to the z to the 6th times ln of 6. And now I just wanted to do one more problem, and then this very long video that I'm making will finally be over. Okay, so number 4. So for this one, we want to find the derivative of y equals x to the 2 pi. Now this one should also be pretty easy if you just apply yourself correctly using the information that you know. So even though the exponent is 2 pi, remember that pi is just a real number. So pi is 3.14159, goes on forever. It's an irrational number, but it's still just a real number. So 2 pi is just a constant. So that's the main thing to realize here. So 2 pi is just a constant. Okay. So how are we going to do this problem? Well, this one's actually a little bit kind of a trick problem. So you might think that this is an exponential, but this is actually a power. All right, so be careful. Careful. This is a power function. So remember, a power is where you have something like x to the a. In fact, let me make a little Let me write this over here so that we can see it. Let me zoom out a little bit. So a power function is something from Calculus 1 where you have y equals x to the a, where a is constant. This is not an exponential function. This is not an exponential function. Remember, an exponential function actually has, instead of having a variable as the base, it has a constant as the base, and the exponent is the variable. This is not an exponential function. Y equals a to the x. Okay, where a is constant, but x is a variable. So for this one, a is also constant. So I just want to point this out because sometimes people can get the two confused. Because all the examples we've done, the actual function was a power function. Not a power function, was actually an exponential function. But this one is actually a power function. Sorry, I misspoke. So because this is a power function, the derivative of a power function is different from the derivative of an exponential function. Okay? So, derivative of power function, well, that's d dx of x to the a equals, well, that's just the rule where you bring the power up front and you decrease the power by 1. So that's going to give you a x to the a minus 1. Okay, so that's the derivative of power, whereas the derivative of an exponential function is the one that we just learned. So d dx of a to the x, where the base is actually a constant rather than the exponent being a constant. So the derivative of an exponential is going to be ln of a times a to the x. Okay, so it is important that you be able to distinguish between these two because they do have different formulas. So you have to use the correct formula based on what part of the problem you're doing. So I just wanted to clarify that. That might also help you with some of the earlier problems I did here. Just so that you can keep powers and exponential functions separate in your mind. Okay, so a power function has a constant as the exponent, whereas an exponential function has a constant as the base. Okay, so here this one is a power function because the exponent is constant and the base is the variable. So here we're going to be using the power formula. So here we just go ahead and bring the exponent out front and we decrease it by 1. So it's actually a really easy problem if you know what to do. So this one is going to be dy dx equals, bringing the exponent out front, we have 2 pi times x to the 2 pi minus 1. dy dx equals 2 pi times x to the 2 pi minus 1. And that's actually our answer. You can't really simplify 2 pi minus 1 because they aren't like terms. So that's your final answer. Okay, finally finished all of that. Thanks for watching this long video.